In this video, we are going to have the definition of a field. What do you mean by extension field? Examples. And what do you mean by finite extension? Transitivity theorem on finite extension fields. So you have first the definition of a field. When you consider F to be a non-empty set together with two binary operations, addition and multiplication. With regard to addition, you need to have 5 axioms, namely closure, associativity, existence of identity, existence of inverse, and commutativity. And the same way, these 5 axioms should be true for under multiplication also. And other than these 10 axioms, you have another one, namely distributive laws. A dot B plus C is A dot B plus A dot C, and A plus B dot C is A dot C plus B dot C. And we also know from the linear algebra that every field is a vector space over itself and over its subfield also. So that is the definition of a field. Now we have the definition of extension field. We say that K, you have two fields, say one is F, the other one is K. When you have K to be a field which contains F, then you call K to be extension of F. You have two fields, one is F, the other one is K. When do you call K to be extension of F if F is contained in K? So that is called extension. And just now we said that K is a field, means it's a vector space. So we can talk about its dimension. So when we have the dimension of K over F to be finite, then we call that dimension to be the degree of K over F, and this is the notation. Degree of K over F is nothing but degree of K over F is nothing but the dimension of K as a vector space over F, and the notation is this. This is the notation. Now, whether you want to have finite extension or just an extension, we have examples, namely C is an extension of R and R is an extension of Q. Now, C is an extension of itself. That is also to be noted, because any element is generated by itself. So, each element is a basis for itself. So, you have your C to be finite dimensional over itself. So, its dimension is 1. When you consider dimension of C over R, when you consider C as a vector space over R, means 1 and I will generate. So dimension of C over R is 2. And when you consider C, you can first, we had only the definition of extension. So C is an extension of R because R is contained in C, and R is an extension of Q because Q is contained in R. So this is just for extension we have. And as for degree is concerned, you have dimension of K over F. Finite means degree of K over F is that finite number. So K is a finite extension if degree of K over F is finite. Degree means dimension. Now C is a finite extension of R because dimension of C over R is 2. So C is a finite extension of R as dimension of C over R is 2. Now we have this theorem: if L is a finite extension of K and if K is a finite extension of F, then L is a finite extension of F. And we are going to establish this. This is a number. This number equals the product of these two numbers. So what is given? L is finite extension of K and K is finite extension of F. What we need to prove is L is finite extension of F. Finite extension means degree will be finite. Degree means dimension. So we will take degree of L over K finite and call it as, say, some M. And degree of K over F finite, take it as some N. So dimension means the basis elements will have finite number of elements. So here degree being M, V1 etc. Vm is a basis of L over K. And degree is N in this case. So we'll take W1, W2 and so on Wn to be a basis of K over F. Now we want to find a basis for L over F. So what could be our choice? You have your V1 etc. Vm for L, and for K you have W1 etc. Wn. So the combination V1 with W1, V1 with W1, V1 with W2, and so on. So it goes V1 with W1 and so on, V1 with Wn. Similarly, if I consider V2, V2 with W1. So like that, when you consider this collection S as this you get. Now our job is to show that these form a basis of L over F. So to show that it is a basis, first of all, we must know that whether it is present in L. So these are all definitely there in L, because these VIs are in L and WIs are also in L. L is a field, so closure holds. So these are all members of L. That we must first assure. So we have that to be true. Now we'll have to show that it is linearly independent and then it spans. So to show that they are linearly independent, the usual procedure is the linear combination is to be considered, and that should be equated to 0. Linear combination of what? We have to consider the linear combination of these vectors alpha, W1, W1, V2, W2. We have actually first row V1, W2, V1, W2, and so on, V1, Wn. So how to give the coefficients? You just see the suffix, so alpha 1, 1. Here 1, 2, so alpha 1, 2, and so on. Here 1n, so alpha 1n plus. So we have accounted the first row. Similarly, second one, V2 with W1, V2 with W2, and so on, V2 with Wn plus, and so on. So again, the coefficients alpha 2 1, alpha 2 2, and so on, alpha 2n, and so on. We have to have alpha here Vm W1 plus alpha Vm W2 plus, and so on, Vm Wn. So this M1, alpha M1, alpha M2, alpha Mn. So the linear combination of these elements in S we have considered, that should be equated to 0. That should be equated to 0, and we have to show that what we need to show is alpha ij's should be 0 for all I ranging from 1 to m, and j ranging from 1 to n. This is what we want to show. Now we are given that L over K is having V1 etc. Vm as basis. So what we are going to do is we will take out V1 from this. So what we have is alpha 1 1, V1 we are going to take out. So alpha 1 1 W1 plus alpha 1 2 W2 plus, and so on, alpha 1 n Wn V1 plus, and in the same way V2 we are going to take out, and so on. Finally Vm we are going to take out, equate to 0. So here what all will come? Alpha 2 1 W1 plus, and so on, alpha 2n Wn. Here alpha M1 W1 plus, and so on, alpha Mn Wn equal to 0. Now V1 etc. Vm, they form a basis. So this is a basis of L over K, basis of L over K. Right. Now we can call it as, say, some A11, something like this, A11 plus V1, yeah, A11 V1 plus, and so on. Some scalar that you have like this. Suppose I name like this, Vm. Now v1 etc. vm being linearly independent, the scalars should be 0, and we must also ensure that they all from our k. It is because you have your w1 etc. wn to be a basis of k over basis of k over f. So you must have these to be members of k, and of course these are scalars from f. And remember, you should not write w1 first and then v1, because when you write, see, because sometimes the students make this mistake that they will take out something is to be taken out, so let me take out w1. No, that is wrong. So we have to have only v1 v2, that should come out. Why? The reason is whatever you have scalars here, they should be from k. If you take the other way around, then you will not have so. So no, it has to be written in this way only. So you have each scalar. Now each scalar should be 0. Each scalar should be 0. So you have, so what you have to have is alpha 1 1. You have to have alpha 1 1 w1 plus and so on, alpha 1 n wn 0, and in the same way last one alpha m1 w1 plus and so on, alpha m and wn to be 0. Now w1 etc. wn, they form a basis of k over f. See, these scalars that should have been mentioned, alpha ij's are from f, because our job is to show that L has a basis over f. So naturally these are to be taken from f only. So w1 etc. wn being basis of k over f, and they are linearly independent, so the scalars should be 0. So all this together will imply alpha ij is 0 for I ranging from 1 to m and j ranging from 1 to n. So the linear combination equates to 0 gives each scalar 0, and therefore S is linearly independent. Next we have to show that S spans L over F. So for that, for spanning part, we have to consider an element X in L. What we need to prove is X is linear combination of elements of S. So to show that, because X belongs to L, X can be, and L has a basis V1 etc. Vm over K. How we can write our X as? We can write that as say some K1 V1 plus and so on Km Vm. Where are these Ki's? In capital K. But what is known about Ki? Each Ki being a member of K, which has got W1 etc. Wn as a basis, K1 can be written as linear combination of what? W1 and so on Wn. And similarly K2 can be written as linear combination of and so on Wn. And similarly Kn can be written as Km can be written as linear combination of W1 and so on Wn. Now comes what should be the scalar. So for that you just go back to this. When you want to have V1 with W1, you had that as alpha 1 1. And here you took V1 out, So what you had was alpha 1 2. So you give the scalars in this way, so that it will be easy for us. And Wn alpha 1n Wn. And similarly for the second one, you take it as alpha 2 1 W1 alpha 2n Wn. And for this alpha m1 W1 and so on alpha mn Wn. Now you substitute all this for K1, K2 and so on. You just substitute here. What you get is this. This is what you will get. Finally, you will get only this. So this is my X. So we can make use of the process that we have used for showing that the S is linearly independent for this also. You just now for the second part you forget about the 0. So finally you will have this to be the linear combination alpha 1 1 v1 w1 plus and so on alpha 1n v1 wn plus and so on alpha m1 v1 alpha m1 vm w1 plus and so on alpha mn vm wn. So we have got, and these are scalars. These scalars are from f. Why? Because k is finite dimensional over f and basis elements are this. So naturally the scalars should be from f. So you have your x being written in this way. We have shown S is linearly independent, S is linearly independent and S spans L. So you have your W in linear combination with scalars. So that proves the second part, and therefore S is a basis of L over L over F with the Mn elements. So number of elements in the basis. How many elements are there in the basis? There are Mn elements. There are Mn elements in this basis. So dimension of L over F is Mn. What is M? It is dimension of L over K. And what is N? Dimension of K over F. So, but this is denoted as degree of L over K, and this is degree of K over F, and this is degree of L over F. This part is very important for later discussion, that whenever we have F, you have K, you have L, L over F is L over K into K over F. L over K, degree of L over F is degree of L over F is degree of L over K into degree of K over F. So that theorem will be used quite often in the rest of the sections. Thank you.